Let's suppose that two autonomous systems connect in two different cities, San Francisco and New York. Let's further suppose that AS1 wants traffic to destination D to enter via New York City rather than via the peering link in San Francisco. We'll remember that all things being equal, routers inside AS2 will select the BGP route with the shortest IGP path cost to the next hop, resulting in hot potato routing. So some routers would select the San Francisco egress, and other routers might select the New York egress. To override this default hot potato routing behavior, AS1 might advertise its BGP routes to AS2 with MED values. For example, if the MED value on the route learned at the border router in New York was 10, and the MED value for the route learned from the router in San Francisco was 20, then instead of performing hot potato routing, all of these routers that would ordinarily be closer to the San Francisco egress would instead pick the route learned via the New York egress, because the preference for a lower MED value comes before the preference for a next hop with the lower IGP path cost. So all of these routes would instead be carried over AS2's backbone network and exit via New York. Thus, MED overrides hot potato routing behavior, allowing an AS to explicitly specify that it wants another neighboring AS to carry the traffic on its own backbone network, rather than dumping the traffic at the closest egress and forcing traffic across the neighbor's backbone. MEDs are typically not used in conventional business relationships, but they're sometimes used, for example, if AS1 does not want AS2 free riding on AS1's backbone network. So effectively, MED allows AS1 to say, yes, I will connect or peer with you, but it is your job to carry the traffic long distances across the country. This mechanism is sometimes used when a transit provider peers with a content provider, and the transit provider doesn't want the content provider essentially getting free transit through the neighboring AS. In the absence of MED overriding any behavior, typically what will happen is a router inside the AS2 would learn multiple routes via internal BGP to different egress points for the same destination D, and it would simply pick the next hop, or the egress router with the lowest IGP path cost, in this case 5. It's very common practice to set these IGP costs in accordance with distance or propagation delay, thus resulting in routers inside the AS picking shorter paths. Now, one problem with this notion of hot potato routing is that a very small change in IGP path costs can result in a lot of BGP routing changes. Remember that it's probably not just one destination that's being routed through the San Francisco egress, but maybe tens of thousands of routes. So a single IGP path cost change can result in rerouting of tens of thousands of IP prefixes in BGP. People have looked at various ways to improve the stability of BGP routing by decoupling the IGP and the BGP in this part of the route selection process.